as like just the general format, it's going to be the same format as your tests are always. So you're going to have a multiple choice section, a short answer section, and then a mathematical component. It's going to be the same proportion. Usually your multiple choice is like a third of your test, or like 30% I'd say. The short answer is usually 30%, and the math is usually around 40% of your test. It's going to be the same for the midterm exam. You can expect similar problems for sure, because as you guys know in physics, the problems are very similar, but situations change a little bit. Or, instead of a box being pulled, now you have like, an object that's not necessarily a rectangular prism. It might be like a cylinder, but it exhibits the same properties. They're analogous. So again, the test will be similar to questions that you've seen on your old tests. So just so you know, some things that are good to study from. Problem sets, tests, labs, and I'd say notes and the examples of doing the notes. Those are your best 4 things you want to study for the midterm exam. You will use a Scantron in the midterm simply because there's going to be more multiple choice than there are because it's a longer test. But it'll still be around 30% multiple choice, 30% short answer, and about 40% mathematical. I will give you I will give you a choice at the end, again, for the math. I forget what the numbers are right now, but I think it's like choose 8 of 10 or choose 6 of 8. I forget which way it works, but you're going to choose a certain amount of problems that you want to do. That doesn't mean, though, I'm just not going to study projectile motion, or I'm not going to study this topic, because those ideas are going to come up on the other areas. They'll come up in your multiple choice. They'll come up in the short answer. So don't just ignore a topic and say, I can ignore that because on the math part, I can omit that problem. Okay, don't fall into that category. Because also what happens if, what if there's 2 problems in there that are really tough and that you want to omit, and then suddenly you didn't study one topic, so now you have 3 types of problems and you can't do that. Okay? So make sure you're studying things evenly. And especially when there's something you don't know. That's what you should really be studying. If, Teresa, you're a pro at momentum and you did so well on that test, you probably shouldn't study too much momentum. Maybe review it, right? But then go back and study the stuff on projectiles or the stuff on energy that you had trouble with or whatever it may be, right? So think about that when you're studying. A lot of students like to study the things that they're good at because it's easy, right? Oh, I can review this. This is simple. It's the stuff that you're having difficulty with that you should really be focusing on. So as you know on the review sheet, what I did was I grouped them by topic. So the first group here that we're taking a look at, this is all just displacement, velocity, acceleration. Okay, so generally it's dynamics. That's really what it is. The study of motion. That's this first grouping here. Now, you're going to see there's a bunch of formulas on the right as well. These are all the formulas that pertain to this topic. Can we quickly go through, just quickly, each formula? And if you don't know it, maybe you want to write it down. But if you're good, then don't worry about it. You don't have to write everything down that I'm saying. But the first formula, V equals x over t. V equals x over t. When would you use this formula? This is what I mean by theoretically what we're going to be doing. When would you use a formula like this? V equals x over t.
If you're given, say, like if it's a problem where this is the same as speed is a d over t, like if they're the same formula, just
S equals d over t is like the speed version, yeah.
So like if this were like speed and you had, distance and time, and then you could find the average speed.
So what's not involved in this problem, James? Well, that's involved in all the other equations.
Acceleration.
Yeah. This is when you don't have acceleration. So let's jot that down, because that's a key. When you don't have acceleration, that's when you can use the first formula, and only then. If there is acceleration, the first formula does not hold true. Please remember that. We learned this first formula when it was called zero acceleration. There is no acceleration. So this is, for example, like James was saying, you're running, right? You run down, let's say you run a mile in 7 minutes, right? Then you run a 7-minute mile, you can come up with your velocity or your speed. We're not even looking at acceleration. We're just looking at general average velocity or velocity overall. So this is like we could even say our constant velocity equation. Constant velocity. If I'm moving and walking across the room with a constant velocity, I'm not accelerating. So again, there's no acceleration involved in this problem. The second equation. Clearly when there is acceleration right away, right? And what does the delta V mean again? Change. So what would you replace it with?
Like VF minus VI?
Yeah, final minus initial. Not initial minus final. Okay, final minus initial. So that delta V is VF minus VI. And that makes sense. Because if your VF is bigger than your VI, when you subtract them, you're going to get a positive number. Well, if VF is bigger, it means that you're speeding up. Right? You're going from a slow velocity to a much faster velocity. Thus, you get a positive answer because you're speeding up, positive acceleration there. Okay? We talked about the fact that you could be moving to the right and have a negative acceleration. And a lot of people had struggles on this on the test. The question on the first test or second test, whatever it was can a boat moving eastward accelerate westward? A lot of people said, no, it cannot. It absolutely can. It's called braking, remember. You can accelerate in the opposite direction. You're just braking. It's like when you hit your brakes. You're driving your car down the road, right? You slam on the brakes. You are decelerating, as Luke just said. You're decelerating, or negative acceleration. Okay, so you can have negative acceleration. It just means you're opposing the motion of the body. Okay, you're opposing the motion of the body there. The third formula, VF equals VI plus AT. This is one of our formulas that's involved that does not have displacement. Look at the last two here. The last two formulas, they do involve displacement here. But the third one here does not involve displacement. So this is really a rearrangement of this formula above. That's all it is. These are the same formulas, really. Again, these two formulas, this one and this one, are really the same exact thing. Okay, and you can do that by replacing delta V with VF minus VI and then resolving for VF. You'll get the third equation there. So technically speaking, I know I've given you both, but you don't need both of them. Okay, you don't need both of them because this is just a rearrangement of this. The fourth formula, though, is a newer one, or is one that does not show up in the others, and this is no longer relating time. So you would use this fourth formula if you're looking at projectiles or objects moving without a time given. So if you have the displacement, and you have the initial and final velocity, or maybe you have the acceleration, you could find the displacement. Now, these last three formulas, before I go any further, they all have x in them. They all have x in them. And that means, we're looking at horizontal motion. But what else could it have? You were just going like this. Y, yeah. You could have the y component. So all of these formulas could be rewritten with y's in them instead of x's. Okay? So that's vertical motion. And then we put those two together to look at projectile motion. Okay, again, I'm not going to go into the math part. We'll do that next week. We'll do projectile motion examples. But just theoretically speaking, okay? So we use these formulas and we can combine them to look at, two-dimensional motion. Motion that is acting on a plane, not just on a line. The last equation here is one of our basic ones, and we usually use this when we're looking for the displacement because it's already solved for x. And when we have the time, initial velocity, and the acceleration. Okay? Remember that the time is being squared at the end here. The acceleration is not squared, just the time. Some of you earlier in the year, I noticed, would lump the AT together and then square it. But you're squaring the time, and then you're multiplying it by acceleration and the 1/2. What's the acceleration on Earth? If we're in a free fall state, we're moving vertically. What is the acceleration? Yeah, for projectiles, negative 9.81 because it's accelerating you down meters per second squared. Okay? On Earth. How does it differ on the moon? How does it differ on the moon? What is it? Yeah, it's much less because the moon has less. What is it? Mass, which leads to less gravity. Very good. The gravitational field on the moon is 1/6 that of the Earth because its mass is much less. Okay, because its mass is much less. Remember, when I'm on the moon, I'm looking at and now that we learned gravitational force, we know that it's Gmm over r squared, right? When I'm on the moon, it's m1 is me, m2 is the moon. When I'm on the Earth, m1 is me, and m2 is the Earth. So the only change in that formula that we learned recently is that m2 changes. It goes from being the mass of the Earth to the mass of the moon. But the mass of the moon is much less than the mass of the Earth, and that's why the gravitational force on the moon is much less than the Earth. That's why it's 1/6 approximately. Okay? That's why you see people like, those cartoons where people are bouncing on the moon. Because you can jump a lot higher because gravity is not pulling down as much. What's that?
Have you ever seen blue shoes?
No. What, do they make you bounce? Is that the idea? Yeah. And it comes from that. What about Jupiter? What about Jupiter or a more massive planet in general? It would have more what? Yeah, more gravitational pull or more gravity. Very good. So the sun, which keeps all the planets in orbit, must have a very large mass, right? And it does indeed have a large mass. Okay, it can keep all the planets in its orbit. All right, that's the first section. Let's go on to the second section. What is the second section all about? One word. Newton or... Oh, there's motion. Yeah, I should say motion because it is motion. But There's one word that comes up in this area that we started to learn in this. Forces, yeah. We learned about forces in this second section. Okay, in this second section. The first equation is Newton's law, F equals ma, which by now everybody has memorized, I know, but it is on your formula sheet. The second one, the second equation, what are you finding? What does Fg really mean? Yeah, on Earth. Now, this formula is still applying on the moon and on, Mars and Jupiter, but what changes in the formula for different planets?
G.
Yeah, little g. Okay? That goes, and I'm saying little g as opposed to big G, okay, because we just learned big G. So on Earth, 9.81, but again on the moon, like 1.6. It's much less value of little g, the gravitational constant on the moon.
When is G negative?
Okay, in the first section when we're looking at projectiles, because it's moving down, we consider G to be negative 9.81. But with forces, we don't have to do that because our free body diagram already points down with weight. Remember, the vector that we draw is straight down for weight. So the arrow is already taking into account the negative. So you don't put a negative 9.81 when you're calculating the weight. Because again, the arrow down is already taking into account that negative. Okay? All right, the third formula. FF equals mu Fn. What is that? What's the deal there? What are those variables? What is it? Okay, there's some surface interactions going on. What is the formula though, I'm asking?
Force of friction is the friction constant multiplied by Fm.
Yeah, the normal force. So let's quickly go some theoretical stuff. Ready? Everybody do this. Put your hand on the desk. Okay? Don't push down very hard. Just like rest it on there. Just go like this back and forth. Okay? Now push down. You're dirty minds. Now push down and try and move left and right. But push down hard. So try and move left and right. Okay. What did you increase when you push down? The normal force, the reaction, right? When you push down, doesn't the table push up harder? When you increase the normal force, you increase friction. That's what this is saying. Friction is proportional to the normal force.
Oh, is that what mu
Mu is a proportionality constant. It's the surface qualities that give you mu, but it's proportional to the normal force. The harder, the more normal force is, the more friction is. Okay. Now, as James mentioned, mu changes based on the surfaces. So let's go through something there. Can mu be negative? Mu cannot be negative. Okay, mu cannot be negative. It wouldn't make sense. Now, mu also doesn't have any dimensions. And makes sense of your answer. What are the dimensions of the force of friction? What are the units of force of friction? Newton. And what are the dimensions or units of normal force? Newton. So if I have a Newton on both sides, there's no way that mu could possibly, Mr. Rusi has it, right? Yeah. There's no way that mu could possibly have any units. If you have Newton on one side and Newton on the other side, they have to balance, right? So if mu had any units, it wouldn't make sense. So mu is dimensionless or unitless. Would mu get lower or higher if I had taken WD-40 and sprayed it all over these little joints in the door over there? It would get lower because there'd be less friction. Okay? So the higher the mu is, the more friction. The lower the mu is, the less friction. Okay? Some examples of low friction materials that I've used. Ice. Teflon. I think that was the two that we talked about that are low. Then we did the lab with felt and cork on the bottom, right? Felt was kind of in between, and then cork was high friction. Rubber would be high friction. Cement and rubber, like outside on the sidewalk, that's pretty high friction. If you almost fell into the street, you could stop yourself, right? Why? High friction. If there wasn't much friction and there was ice out, what would happen? You would slip. That's when there's lower friction. I was in Michigan, I was telling you guys, for Christmas break, and it was hysterical. I didn't have my snow boots, I forgot them. So I was wearing like Nike sneakers. And it was like a sheet of ice up there because it had snowed so much. So we were walking up to University of Michigan Stadium the morning of the hockey game, and it's all uphill, the entire walk from where my friend lives. So we're walking up the hill, and I was literally, ever see the cartoons where people are like slipping out and they're like running in place? I was like doing that. It was so difficult to walk uphill. It was unbelievable because the mu value was so low.
Did you
Okay?
crease them? Yeah, friends.
Yeah, I do have friends.
Chill, did you crease them though?
Did I what?
Did you crease their shoes? Crease.
I don't know what that means. What does that mean? I'm sorry.
Crease your shirt, crease the shoe. Crease is in get a crease in an object, as in fold.
I know, but of course my shoes have creases in them. I run with them, so I don't know. All right. Next part. Folks, focus. Don't lose focus. Come on. This next part here, fx and fy. Fx and fy. What are those relating? Fx equals f cosine and fy equals f sine. What is that? Different axes involving theta, sure. Involving theta.
Motion on ramp.
Say again?
Motion on ramp.
It can be used in the motion of a ramp, sure, but in general, though, I'm asking. In general, what are these formulas used for? What at angles? Forces applied at angles. So imagine if I was, remember we did this example with pulling on a desk. I think you came up, right? We took a picture and then drew the forces on it. If you're pulling on a desk at an angle, here's the angle right here between my hand and the horizontal. This is theta. Again, if I'm pulling at an angle, I'm not pulling up and I'm not pulling out, I'm pulling both, up and out. So I have to use this vector, these vector components to come up with that. And the simple example, remember, is something like if you're pulling on a sled in the wintertime. If you've ever pulled on a sled, and imagine like somebody sitting in the sled, obviously, if you pull hard enough, the sled kind of comes up off the ground a little bit, right? That's because you're pulling at an angle, so you're technically pulling a little bit vertically, causing it to lift up. But when you're pulling this way also, because it's at an angle, don't you start to move? So you're pulling up at an angle, so the sled lifts up and also moves to the right. Okay, it doesn't lift up off the ground completely because of gravity, but it does move to the right because there's very little friction. Okay, very little friction in the snow. Next section. Work and energy. Work and energy. What was the whole gist of this section? What was the gist of this section with work and energy? Okay? You put in work, and what does that do as a result? It causes an object to? Yeah, to move or lose energy or gain energy. So, if I were to pull on this table, the work kinetic energy theorem tells me that if I pull hard enough and put enough joules of energy into it, the object will change kinetic energy, or it will start to move. It'll go from no kinetic energy to having some kinetic energy. Okay? That was the beginning work and energy part. What about section 5.3? Section 5.3. What was the idea there? Who can explain that conservation part?
The energy in the beginning is going to be the same as the energy in the end.
Very good. Which is analogous to conservation of momentum. Momentum before equals momentum after. So here, conservation of energy tells us that the energy beforehand equals the energy afterward. The energy before equals energy after. Let's quickly look at our equations. The first one up here. Work equals FD cosine theta. FD cosine theta. F is the force. D is the distance. Okay? And we look at only the horizontal force being applied, so we put in the cosine theta there. Okay, the cosine theta. So the amount of work done can tell you, if you know the force, how far you moved. If I know that I've put in like 20 joules of work today in moving this desk, or in the last few minutes in moving this desk, and I know what the force I applied was to do that, I can find the distance the desk would travel. Okay? James?
Yeah, before I go to using alternate formulas for finding work, why is cosine theta in the formula?
Because you are looking at the work done along one direction.
Right.
Okay? So if I'm even pulling at this angle, and I'm looking at the work done to traverse in this direction, the distance traveled is only in the x direction here. Right? If I pull on this desk, even though it's at an angle, James, which way is it going to move? In the x direction. So I use the angle theta, remember, is the angle between the force and the direction of motion. So if I'm pulling this way, and this desk, imagine, well, that's a tough example because gravity would work against us, but imagine I was pulling on a rope. Remember the mine shaft example? Imagine they're milling some coal on a mine shaft, and a rope is being pulled at an angle. Which way is the mine moving, though, or the mine shaft is being lifted up, right? So now the angle would be this angle cosine theta right here, as opposed to earlier the angle was down here. So you're looking at the direction of motion only along the vertical or the horizontal.
But how does multiplying by cosine theta correct the angle?
It doesn't. It gives you the component along that angle. Remember when we derived it with our triangles, really, James. We looked at how cosine theta gave us the one component, sine theta gave us the other. But now we're using cosine theta and just saying, always look at the angle between the direction of motion and the force. So if it's moving this way, but you're pulling this way, here's the angle. But if we're moving this way and you're still pulling this way, here's the angle now. Whenever you have the angle between them, you could always use cosine theta. Okay? You didn't get to too much of it in your trig class yet or in the Algebra 2 class yet. But if you study more physics, you'll see that you could always use cosine theta, really. You don't have to ever use sine theta, provided you have the angle that's between the force applied and whatever else you're looking at. All right?
So you're trying to find the work on the end where force is applied rather than where things are moving. Like you're trying to find on your end of the road. Like that's why you apply the angle.
You could think of it that way, yeah, but I would just generalize and say you're finding the work done in one direction. Okay, in one direction. The second formula is kinetic energy. These kind of questions on the test, here's a good conceptual multiple choice for you. What happens to the kinetic energy of an object if the velocity doubles? If the velocity doubles. So if I put a 2v here, what happens to it? It becomes 4v squared, so it quadruples. Remember that, that we talked about that in the last section with Fg equals gmm over r squared. We said what happens if this doubles or this halves or stuff. Same idea here for these kinds of questions. Okay, especially when you see a square. When you see a square and something doubles, it really goes up by 4. If it's squared and the velocity, say the velocity tripled, this would be a 3v and it would make it 9v squared. It would go by a factor of 9. Kinetic energy of an object, the object has to be in motion, okay, to find kinetic energy. If it's not moving, it doesn't have kinetic energy. Now, we're thinking on a macroscopic level. I'm currently not moving, so you'd say I have no kinetic energy. But obviously my molecules are moving because technically speaking, temperature is a measurement of kinetic energy. So you do have kinetic energy always, but when we're looking on a physics macro scale, on a big scale, we could say that this bottle here has no kinetic energy. Okay? It has no kinetic energy. Although really it does, at some level, has some motion of its molecules. But at that point we call that internal energy, which we haven't even talked about. That's more like a little bit chemistry. Okay? Looking at the energy between the bonds and breaking of the bonds and the moving of the bonds. In this, though, we're looking at kinetic energy of objects on a bigger scale. The work kinetic energy theorem is listed right here, and that tells us that the work done on an object is equal to the change in the kinetic energy. So you could take this formula here and set it equal to 1/2 mvf squared minus 1/2 mvi squared, the change in kinetic energy. Okay, and I'll write that out at the bottom over here so you see what I'm saying. You could say f d cosine theta, that's not minus, that's times, equals 1/2 mvf squared minus 1/2 mvi squared. That's the work kinetic energy theorem. It's not written out as a formula because you have all the formulas right above it. These two formulas are what go into the work kinetic energy theorem. So I'll give you the work kinetic energy theorem, W equals delta KE, but this is really what it is at the bottom here. Okay? If an object comes to rest, it has no what? So what could I do to that equation? If it came to rest, what do I do to simplify that equation in red at the bottom? Yeah, you'd cross out this portion for sure. If it comes to rest. What if it starts at rest? You would cross out, the other portion over here. If it started from rest, this would not exist. But remember, if this finishes at rest, there's still a negative sign here. A lot of you are forgetting that negative sign in the middle. When this goes to 0, so when this part goes to 0, this negative sign still applies. It's still tacked on to the right-hand portion because it's really 0 minus some number. 0 minus any number that is positive will end up being negative. The next formula after the work kinetic energy theorem, potential energy equals mgy. What does that relate? What does that relate? The what of an object? What's important for potential energy? Gravitational potential energy. The height of the object. The vertical location. Okay? So if I start up here on this desk and I end up on the floor, I have lost or gained potential energy. I start at the desk, jump off the desk and land on the floor. I have lost or gained the potential energy. Lost, because I'm starting at a high potential energy, a higher height, and I'm going to a lower height. James. Mike.
This is more theoretical than anything else, but it's always measured from the bottom of whatever object it is. Like, even if it was like...
As long as you're consistent, James. It's technically the center of mass.
So if it was like a 3-kilometer high pillar of stone, sitting...
It would be a kilometer and a half is technically the height of it, the center of mass. That would, yeah, that's an interesting question, yeah.
How does an object like gain potential energy?
So if there's some sort of energy done to it or given to it, and that's where conservation comes in the next one.
Like an outside force?
Exactly.
You can't gain it by yourself?
Yeah, exactly. You can't just gain potential energy. I need to actually push with my leg, apply a force. So I can apply an outside force in a sense, sure. Or remember the spring? If you load a spring and release it, you're giving it energy by storing it in the spring, and then that energy gets converted to potential and kinetic energy. Okay? So a transfer, in a sense. Transfer. And that's what the next one is that we were just alluding to here. Potential energy that is in a spring. 1/2 kx squared. Now, what is k in this problem? Good. The rigidity or the spring constant. Both are correct. Very good. If k is a higher value, it's a stronger spring. It takes more force to compress that spring, but it loads or stores more energy. So if I'm at a pinball or an arcade and I use a pinball machine and I pull back on that, I'm applying a force, right? And I'm storing energy in the spring. Let's say it's a really old pinball machine. It's probably a weak spring, right? So you can just quickly pull back and it shoots the pinball off. So the spring, as k goes up, becomes more rigid or strong. So it takes more force to store that energy, but then it actually has more energy stored in it because it's a stronger spring. A strong spring example would be like on like an 18-wheeler or a truck, right? A big truck that's driving would have pretty strong springs because its suspension system has to allow for a lot of mass to vibrate or oscillate up and down. When you hit a bump, your car is oscillating, right? That's what's happening. It's vibrating, okay, back and forth. If you have a really weak spring and it's a really heavy truck, that spring will snap or too much force will be applied to the spring. So you need strong springs there versus like your bicycle. Your bicycle does not really need any strong springs because there's not a lot of mass on it, okay, relatively speaking. And your pen, remember the pen was the other example? Like your click pens, those are really weak springs because you're not applying a lot of force to them at all. The next formula, I'm sorry, we should stop and say, what is X in this formula? What is X? How much you compress or stretch, right? Or stretch. Not the displacement, really. It is technically the displacement of the end of the spring, sure. But that's how much you compress it or extend the spring really is. All right, what is this formula here? MEI equals MEF. What is it really?
Mechanical energy initial equals mechanical energy.
Yeah, and what is mechanical energy, Nina? Overall, what could be mechanical energy? What could we plug in there? What could you start with? Imagine it's a spring loaded. You would only have spring energy, right? Okay, but then what could you end with? What kind of energy? If it gets launched to a height up here, what energy could you end with? Kinetic and potential, right? So this formula, MEI equals MEF, is relating the energies that we just saw. Kinetic, potential, and potential in the spring. This is the easiest formula to ever use because all you need to do is look at the problem and see what's happening. So let's start with a quick example. No numerical, but just theoretical. I start on a cliff, but I'm in a spring, loaded. Imagine I'm like a stunt devil, loaded in a cannon, on a cliff. I get launched off that cliff. And at some point in time, I'm still traveling, and I end up right here. And I freeze frame for a second. Okay, so I still have some height off the ground, God bless you, and I'm still moving. So what are the energies in this problem? Again, I start on a cliff, in a loaded spring, and I'm going to freeze frame at some point in time here, where I still have height and I'm moving. What kind of energies are associated?
Potential there, potential and kinetic.
Good. So both potentials here though, right? Because you have height and you're in the spring both.
Yeah.
So both potentials in the beginning, and then good, Luke. I keep saying Luke. Both potential and kinetic energy at this point in time. Once I hit the ground though, I have no longer any what? Yeah, well, kinetic and potential, really. I have kinetic the instant before I hit the ground still, remember? Because you still have your impact velocity. That instant before you hit the ground, you still have some motion. So you could say you have kinetic energy there. Okay, but you don't have potential energy anymore because now you're at ground level.
How do you have potential energy when you're on the ground?
No, in the beginning, we're on a cliff and you're loaded in a spring. That was the beginning point. So you have potential spring and potential height, both. At the end of the problem, you'd have only kinetic when you're about to hit the ground. Only kinetic when you're about to hit the ground. Even though there's little gaps though, right? Like I'm about to hit the ground, there's a little height. We say there's no potential there anymore because you're on the ground.
So like, if you keep investing on this coin, does it have potential energy relative to the surface it's resting on, seeing as it will fall as soon as it moves?
That's your moment of inertia. That's rotational energy. It's a little different. You're talking about a cube, you said, right? Cube?
Yeah, because I actually got one question wrong on square. I listed potential energy and it was loaded in the spring on ground level because it was like on an angle.
Ah, I see what you're saying. Because you were looking.
So.
Yeah, well, if it's loaded in the ramp though, and we consider the ground level to go through the center of the cube, and I'll try and be very specific on your midterm because I think there was a little ambiguity there with the ground level. And if it's going through the cube, then we'd say there's no potential energy. But I get what you're saying for sure. But that's more a moment of inertia. It's a balance there, okay? And that's because the angle is going to pull it down or pull it to the side, whatever it may be. The last part here, power. What is power? What is power? And you could use that first formula to help you tell me what power is. But don't just read the formula, obviously. But what is power really? And this is one of your multiple choice in your test. A few people got it wrong. I was a little bit kind of confused by the end.
So the amount of work that happens over an interval of time.
Yeah, over an interval of time. Good. So what do we say when it's over an interval of time? We call that the rate, right? So what would you say?
The rate of work.
The rate of what? The rate at which work is done, let's say. Okay, power is the rate at which work is done. So, I could move this desk across the room by dragging it, right? And do a certain amount of work. Luke could do the same thing and move it across the room and do a certain amount of work. We could do the exact same amount of work. But if he does that faster, he has more power. That was the example we talked about with like the weightlifter. Okay? A weightlifter that lifts, say a dumbbell, doing like a power clean from the ground, lifts it up to his head in like a certain amount of time, uses a certain amount of energy, does an amount of work. Somebody else doing the same thing does the same amount of work, but their power differs depending on who does it faster.
It's probably because
Okay.
works out.
Yeah.
That's probably why it is. Most likely. Okay. Now, the other formula here relates power and force and velocity. If you're applying a certain amount of force and a certain velocity, you generate power. Can you open that back window a little, Tristan? Because I know we're getting a little... Trust me, guys. I know when it's warm, people get a little bit like, especially when you're reviewing stuff that's not new. What's that?
What?
Yeah, during the what's it called? After the section on power, we're going to look at this next section, which we recently did. So this should be fresh in your memory, right? So this first statement here says that momentum P is equal to the product of mass and velocity. So the person's mass and the person's velocity is what affects his or her momentum. The second equation tells us that the change in somebody's momentum, is equal to the force applied over a time period. What was this called? What theory was this called? We called it.
MIT.
Yeah, what did MIT stand for? There it is, very good. Momentum impulse theory. And here's what momentum impulse theory tells us. It tells us that the change in momentum is equivalent to the impulse. Impulse is F times T. That's what impulse is. F times T is indeed an impulse. Okay? So it's like, imagine you drop from like a 2-story building, but underneath you they have like a net or a harness, something to catch you and give a little bit. Because that harness gives a little bit, it takes a lot of time, so you feel less force. This was the example that we kept talking about, where if you have, imagine you catch something, right, and you catch it with soft hands, versus somebody throws you something and you just catch it like this. It's going to hurt if you just catch a baseball that's thrown at you like in high speed if you just catch it with your hand. But if you go like this and catch it, you give a little bit. Because again, you're increasing you're increasing the time period you catch it with, and therefore the force you feel goes down. Because the change in momentum is not changing at all. If I catch it and stop it this way versus catching it like this, it's the same change in momentum. It went from 60 miles an hour to 0. Either way, whether I catch it by like this or catching it like this. But when I catch it and give a little bit, it takes more time. When there's more time involved, there's less force involved. So you don't feel the impact in your hand. The third part is analogous to our mechanical energies, right? Momentum before, you're right? You're good? Momentum before equals momentum after. Inelastic versus elastic. Somebody tell me the differences. Inelastic versus elastic. Don't eat so fast.
Elastic is when two objects stick together, and then elastic is when, like the pool, you open it up.
You okay? So, you alright? So inelastic, listen, come on. Inelastic, as Lou said, is when the two objects stick together or merge, okay? Or you jump into like a shopping cart, you start going down a hill in a shopping cart. Don't do that at home, please. But I know you probably have. I have too. I'm just saying, don't.
I fell over in the cart.
I would assume you would eventually. Yeah. Too much rotational inertia, like the cube. Now, with inelastic, hold on one second. With inelastic, there's a loss in kinetic energy. Is that what you're going to say?
No.
Sorry, Gio. So Gio, tell us.
No, you stole my thunder.
There's a loss in kinetic energy. What about elastic?
It's conserved.
Yeah, energy is conserved in elastic collision, in perfectly elastic. In real life, we are somewhere between those two. Imagine, a collision between me and this desk, right? I hit the desk. I'm clearly not stuck to the desk. That was elastic. But there is some energy loss there. The sound that you heard, the friction, there's energy that's lost. So in real life, we're in between elastic and inelastic.
But in a scenario like a pool, it's very close to being fully elastic because
Absolutely.
there's no deformation in the ceramic.
There's no deformation. The sound is definitely loss of energy. But besides that, there's very little friction going on. Same thing with a hockey puck. A hockey puck and a hockey player hitting the puck. It's a very close to being perfectly elastic collision because of the low friction. Okay? And the last section we just did, centripetal acceleration is v squared over r, and gravitational force g m1 m2 over r squared. I'm not going to go into a lot of detail about that because we literally did that this week. Okay? Your two given constants are here on the bottom. You don't have to memorize them, obviously. And then at the very bottom of this document, I put what I said before, the stuff that you really should study.
On the test, I got scared because I didn't remember what G was equal to, base G.
But then you looked at the formula sheet and you were like,
Now for 5 minutes, and I was like, whoa.
it's on there.
You're tracking.
All right, you found it though on the sheet, right? Good. James, question? I saw a hand come up somewhere in the
We're
back.
doing the last minute, remember?
Are we going to get the test back that we took before the gym?
Yes, absolutely. You'll get it back latest on Monday. I was trying to get them done by today, but I didn't get a chance to finish them all, and 5 people didn't take it yesterday, so I'm kind of going to wait until Monday. Okay? All right.